Welcome to Study Loop.
This is chapter 21, problem number 92. Q factor can be defined as the voltage across a capacitor or an inductor of the voltage across a resistor at resonance. The larger the Q factor is, the sharper the resonance current will be. In part A, they want us to show that the Q factor is given by 1 over R squared root of L over C, the inductance over capacitance. So we know the definition of Q. It's given to us in the problem. It's either the potential across the capacitor over the potential across the resistor, or you could use the potential across an inductor over the potential across the resistor. So both are valid. Both are going to take you to the correct answer. Let me pick the first one here. So, now, the potential across the capacitor is at the resonant. Then we have the resonant current times the reactance of the capacitor, right? Where we know that the reactance of the capacitor is 1 over 2 pi f capacitance. So I'm just going to put everything back in this equation. So the Q factor is going to be equal to I resonant and X C, which is, right, let's write it, 1 over 2 pi f c, and in denominator I still have 1 over times 1 over VR, right? VR, as you know from Ohm's law, is going to be the I resonant, right, times the resistance. Now I resonant and then times resistance. So the currents are going to cancel each other out, but the Q factor is going to be 1 over 2 pi f c r. Now I want you to pay attention to what f really is. F is the resonant frequency, and it's given to us as 1 over 2 pi 1 over L times C, if you remember this equation. Now, when that's the case, then let's plug in for f in the Q factor equation, right? So I'm rewriting the Q factor equals then 1 over 2 pi times f, which is 1 over 2 pi square root of 1 over LC times C times R, right? So 2 pi's are going to cancel each other out. What we have then is 1 over square root of 1 L times C R. Let's put the C back in the square root. Then we're going to have to take the square of it, right? So it's going to be equal to 1. Instead of 1, now we have C squared, because if you take the square root, it's C that comes out, divided by L times C times R. 1 C's are going to cancel. So what we have is 1 over C over L R. Now, if we take the inverse of denominator, right, it's going to be, well, 1 over R, it still is what's staying here, the resistance, times square root of L over C then. So there you go. We proved that the Q factor was given as 1 over R times square root of L divided by C. Now, the answer to part B. At a resonant frequency of 1 megahertz, so F resonant is 1 megahertz, what must be the values of L and R if the Q factor is 650 and C is, the capacitance is 0.01 microfarads? Right? It's very straightforward. So first, remember again the resonant frequency equation, 1 over 2 pi square root of 1 over L times C. If we take square root of both sides, then resonant frequency squared is going to be equal to 1 over 4 pi squared times 1 over L times C. Now, we know everything in this equation other than L, so let's isolate L. L then is going to be equal to 1 over 4 pi squared times C times F resonant squared, right? So here, then L is going to be equal to 1 over 4 times 3.14 squared times 0.01 times 10 to the power of negative 6 farads times the resonant frequency is 1 times 10 to the power of 6 hertz, but we're going to take the square of it. So then the inductance is going to be 2.53 times 10 to the power of negative 6 henries. Very good. Okay, we calculated what L is. Now, what about R? In order to get to R, let's remember the definition of Q factor. We proved that Q factor equals to 1 over R times square root of L over C, right? So in this equation, now we know what the inductance is. We're given the capacitance. We're given the Q factor. The only unknown that we have in this equation is the resistance. So then let's solve for it. Then R, if you multiply both sides by R and divide both sides by Q, right? These are going to cancel out. These are going to cancel out. So what we have is R equals 1 over Q factor times L over C in the square root. Then Q was given to us as 650. So times square root of L, we calculated it to be 2.53 times 10 to the power of negative 6 henries divided by the capacitance is 0.01 times 10 to the power of negative 6 farads. Then our resistance is going to be 2.4 times 10 to the power of negative 2 ohms.